Welcome back. In this video, we're going to be dealing with a discussion involving the characteristics of concrete as a material. This will include things such as the stress-strain relationships and a little bit of proportioning details and some of the more general information of the material itself. At the end of the video, we'll also be getting into steel design should time permit. So to start off with, we'll talk about some of the concrete properties that we need to be aware of as we start to begin our study into the design of reinforced concrete structures. All right, so the first topic will be in the area of manufacturing. Okay, as we've talked about previously, the composition of a concrete material consists of cement, sand, coarse aggregate, and water. All of those mixed together appropriately make up what we know as concrete. Okay, so there is a difference in the terminology as well. Cement is a material. In public, the less informed will sometimes refer to a sidewalks as cement sidewalks or cement patios. That is an incorrect statement because cement is simply just one material of the composite mixture known as concrete. So now you'll be able to make corrections, but be gentle when you do so. Okay, when we get into proportioning, okay, there's a water cement ratio law known as Abrams water cement ratio that basically says that the lower the water cement ratio, the higher the strength. But there is a certain minimum amount of water that is necessary, and so that's what kind of got us to our general parabolic distribution, although it's not really truly a parabola, but there's a peak value. So this gets you to your optimal strength, and then as I add water or I start to decrease, if I pull out water cement ratio versus this F prime C value. Okay, so and this is a bit of a danger because in practice, water improves the workability of a concrete mixture as you're trying to place it into the forms and around all of the rebar. And so you've got to be very, very careful of ways of getting workability without reducing strength. The easiest way is to add water, but when you start getting into more advanced mixes, you can start putting additives that increase workability without doing that. And so there are some correctives. Things as additives known as water reducer or super plasticizer or things like that can greatly improve the workability but not affect the strength. But again, it's easy on a job site to grab a hose and just add water to increase the workability, but that's a danger that you've got to be always aware of. Okay, one measure of the workability of this is to do what we call a slump test, and that's basically I have a cone structure and I put the concrete into the top of the cone, and the cones have a standard set of dimensions, and then when you pull the slump cone off, the pile that's inside the cone falls a certain amount before it stops. Okay, and you can measure, it's a 2-inch slump, meaning that the peak of the cone came down 2 inches, or it's a 3-inch slump. It can be a measure of the workability. Generally, the higher the slump, the better the workability. But you also have to be worried about, if your slump gets too high, that maybe I'm starting to, not unbind the concrete materials. You can segregate things out, and segregation in concrete is a huge issue that we want to be worried about. Okay, now normally for building construction, we like to have a slump somewhere in the neighborhood of 3 to 4 inches. Okay, some of the major basic proportioning, and again, a lot of this depends on what F prime C that you're after or what the material availability is that generally we like to have 1 pound of cement per cubic yard of concrete. Okay, and that our proportioning of this will be 1, 2, and 4. Okay, so that it's 1 part cement, 2 parts sand, and 4 parts coarse aggregate will make up a standard concrete mix. Okay, max aggregate size is a factor in a lot of things, and that you'll hear this term thrown around, and that has to do with the size of the coarse aggregate. Typically, smaller max aggregate size results in higher strength because there are fewer failure planes in the stone. Okay, but you can see all the way up to 1/2 or 3/4 of an inch in some applications. This is an issue though for the placement of your rebar, right? Because if I have bars that are too close together, it's possible that if this is a bar and this is a bar, I could get an aggregate that wants to land and it can actually bridge over those 2 bars because it can't fit through the span, and so we can end up with air pockets and voids that will greatly affect our strength as well. So this becomes kind of an issue. All right, now the Abrams curve that I showed you looks something kind of like this. Okay, we've talked about adding admixtures to help with workability. We can also do something called air entrainment, and that also improves the workability, but does decrease the strength on those. So on this axis, I've got the compressive strength, and in this case, I'm measuring it in PSI, and for correlation, I've got it also in the SI units as well. And then the water cement ratio looks something kind of like that. Okay. Now, again, this thing it actually kind of falls off very fast back to zero when I don't put any water into things. So there is an optimum point that starts to look. Now, this is, there are different types of cement that have different characteristics. This is what we call a type 1 Portland cement, which is probably the most common. But you can also do type 3 cements, which give you higher early strengths for the same F'(C), and that's often used in the precast industry. So depending on your application, the type of cement is an issue. And again, we're not getting too much into the actual material characteristics, but we do need to be kind of aware of some of the terminology and the overall basic behaviors. Okay. Now, what you want is you have to do enough mixing to get a uniform mix that get the sand and the aggregate and the water evenly distributed throughout without falling out. If I over mix it, though, what happens is the coarse aggregate will fall to the bottom, the sand will fall to a little bit lower level, and you get kind of this layering or segregation that is not a good thing for strength, because we're wanting a uniform mix throughout. Okay. This kind of goes along with some of our assumptions about concrete, for basic mechanics, where we had linear, elastic, isotropic, homogeneous. Well, this is an attempt to try to get to the homogeneous part of that assumption, which allows us to apply our statics principles. Okay, if I don't have that, then things start to break down, literally. Another issue in the manufacturing process has to do with the conveying. Okay, for ready-mix concrete, it's generally made at a plant and hauled by truck. Well, again, the location of the plant with respect to the job site, I can't put concrete on a truck and expect it to be in the same condition 2 hours later if that's a real long haul. In fact, most of the time, you like to get a hauling distance that at most is 30 minutes to 40 minutes from the time that it's mixed in the plant to the time that it's placed in the forms. Otherwise, concrete starts to set and it gets harder. It starts to harden. It's what we call the set time on it, and that can be a major, major issue. For precast facilities, often they have a plant that's on site, okay? But generally the conveying procedure, though, is we have a truck and then a chute and then some sort of cart or pump or conveyor that gets it onto the specific form. Imagine the challenges associated with placement when you're doing a multi-story building, and you're 18 stories up. How do I get the concrete from the ground up to there? So there's some challenges with that. And again, that's kind of beyond the scope of what we're looking to talk about in this lecture. Okay. Placing, once we get it to the site, then I've got to get it into the forms, and so that gets us into issues with compacting, and so often there's some sort of vibration that has to take place in order to kind of work the material down into the forms, and that can be done with either internal vibrators or external vibrators. An internal vibrator would be kind of like a wand. It's kind of a vibrating rod that you stick down, and then it starts to kind of vibrate and shake the mix so that it moves down and settles in around the rocks. But again, if I over vibrate, then I get back to the segregation problem. Okay, but it does help significantly with preventing what we call honeycombing, which is the entrapment of air pockets. And it'll kind of, you take the forms off and you got these big air voids in there. It kind of looks like a honeycomb pattern in spots. And that's our goal, is to prevent that, because that also affects our strength distribution. If there's no concrete, because there's an air pocket, then I can't have stress transfer across an air pocket. Curing is, once it's placed, then it's got to sit undisturbed, usually for at least 7 days before being exposed. But more often, we try to have curing conditions in place for a lot longer than that. Okay. Better curing helps control moisture evaporation off the surface, which is usually leads to better shrinkage control. Okay, but we also want to maintain the temperature, because the temperature of the concrete when it's placed. I can't place concrete in sub-freezing temperatures. I guess I could, but you want to be very careful, because freezing of water while the concrete is wet can greatly destroy the material interlocking that occurs during cold water. So if you're pouring in a cold temperature, then you've got to come up with some sort of arrangement to make sure that the concrete doesn't fall below freezing. And that can be done by, generally by covering it or applying, heated water, or even some sort of external heating source, or even special admixtures which will prevent the water from freezing. Okay, if I have bad curing of this concrete, I can lose as much as 50% of the concrete strength as a result of just poor curing characteristics. All right, now, the next topic has to do with the compressive strength. Okay, and by far this is the most important characteristic, and we often call this, the one we're after is the 28-day compressive strength, and that's called F prime C. And you'll see this in just about every formula involving concrete design. Okay, the way that we evaluate the testing, the compressive strength, is we do what we call a compressive test or a cylinder test. Okay, and this test is standardized. There's an ASTM spec that governs this, but the standard cylinder is a 12-inch cylinder that's 6 inches in diameter, okay, and has a weight of approximately 30 pounds. Okay, again, that's for normal weight concrete. Okay, and so that would be our standard cylinder size for the compressive strength. Okay, now, another factor that will start to affect us is, my page is squared away here. Okay. Okay, is kind of a correlation between F prime C and the age of the concrete. And so for a type 1 cement, the general curve looks something kind of like this. At 7 days, generally the strength of the concrete when you test the cylinder is 60% of F prime C. Okay, at 14 days it increases, and by the time you get to 28 days, you're up to about 85%. And generally that's what the value that we're looking at. Now, obviously, F prime C, when I call the ready mix company and say I need 4,000 psi concrete, I do not get a material that is exactly 4,000 psi whenever I test it. I mean, I may get something as high as 5,000 or 6,000 as a result, okay, because the provider wants to make sure that you get that as a minimum value. But when I design for it, since I don't know what I'm getting, this is what I spec as the minimum. Okay, but you can see kind of the general relationship for how concrete gain strength over time. Now, there's been research that has shown that for the 28-day F prime C value, that it's the F prime C at any given time t, where t is this horizontal axis, can be approximated by the 28-day prediction of F prime C, okay, and then multiplied by t over 4 plus 0.85 t. Okay, all right, and so that will be kind of our prediction for based on strength. Now, again, typically what we do is we pour specimens, multiple specimens at different times, and we'll do a 7-day test and a 14-day test and a 28-day test, and I'll manually plot this and know what my strength is looking at there. Okay, now the ASTM spec that's used says that the rate of loading should be approximately 2,000 psi per minute for the test. Okay, because concrete behaves differently under fast loads than it does under very slow loads. Okay, so this is kind of the standard that puts us all on the same page when we start reporting those values. Okay, and then the standard for curing is typically what we want is a moist curing, meaning that it's a high humidity. This helps prevent the shrinkage. It's basically 100% relative humidity, and then the curing conditions should be about 70 degrees Fahrenheit. A lot of times what we do with moist curing is that we'll get the initial set, and then we can actually submerge them in some sort of water bath, okay, and that will ensure 100% humidity, and that will reduce the shrinkage amounts in our cylinders. Okay, now the quality control of concrete is kind of important. And so in Chapter 26 of the 14 edition of ACI 318, and in conjunction with ACI's 301, okay, they basically say that since the curing condition on a job site is not as good as it is in a laboratory, ensuring the curing conditions is very, very difficult, okay? And so the compressive strengths of concrete in the actual structure will be vastly different than what you get in the lab. Okay, in fact, they'll often be less than the tested strength, because again, we said that the curing can affect concrete strengths by as much as 50%. Okay, and so what we do is that we can to compensate for this difference, the job specified concrete strength, which is listed as an F prime C sub R. Okay, we can actually do some calculations to kind of correlate, what is a lab tested cylinder to what is actually in the structure. All right, and so this formula is F prime CR is equal to F prime C plus 1.34 K times the standard deviation of all of the samples of what you're taking. Now, this K factor has to do with a coefficient that's based on the number of tests that you're performing. Okay, and so for, if I do 15 tests, then K is taken as 1.16. If I take 30, then this is 1.0. Now, this 30 may look familiar if you're in a probability and statistics class, as this is kind of the minimum sample to be able to approximate using a normal distribution. This is part of the central limit theorem, is where that 30 is coming from, and that's what this model is calibrated to. Okay, so that's one calculation. Okay, or I can approximate it, for concrete strengths that are less than 5,000 psi or greater than 5,000 psi by these formulas. Okay, and so the thing that's advantageous to us here is that, again, I've got to know the standard deviation of the samples, and you can see this is that coefficient, and you may recognize that as being kind of a confidence interval probability for the upper bound of this. Okay, so for less than 5,000 psi, the formula is slightly different than it is for these higher strengths. Okay, because when it gets harder to hit higher strengths, but I also tend to get a lot higher F'C values on higher strengths. I call for a 10,000, I may get a 12, whereas if I call for a 4, I may get 4,500. And so that becomes a difference in these. And you're allowed to, based on the quality control, take the larger of those two values as your F'C for the estimate in the site. Okay, as kind of a predictive model. Okay, now, if you don't have any records for the test data, then you have to modify your formula. This is, again, if I don't know what my standard deviation is for the mix, if F'C is less than 3,000, then you're going to take F'Cr as being F'C plus 1,000 psi. Okay, and if it's between 3,000 and 5,000 is your F'C value, I'm going to add 1,200. And then if I'm over 5,000 PSR, then I'm going to add 700, and I'm going to increase F'C by 10% or a 1.1 factor. Okay. All right. Now, typical values of F'C include for beams and slabs, typically you're in the range of 2,500 to 5,000 psi. Okay. Like I say, 4,000 is probably the most common. So we like, 4,000 psi is typically what's spec'd out here. Okay. For footings, it's more toward the lower end of this. For columns, though, again, because F'C is related to stress, if I have a very big, massive column, maybe architecturally it isn't as appealing. If it's a slender column, it's more graceful and more elegant. Okay, well, as I start to decrease the area of the column, I need a higher F'C to do the same work for the same load. Okay, and then for pre-stress and precast, they often spec a higher F'C because if I spec a higher F'C, my release strength at 1 day is going to be higher than if I spec'd a 4,000, and we need a certain release condition or a certain strength of concrete at the time of releasing of the pre-stressing force. Now, again, we're not going to talk a lot about pre-stress and precast, but it does have its role in kind of how F'C is established and how mixes are rated and designed, based on the type of Portland cement. Okay, all right. Now, the heart of what we do in concrete design falls back to stress-strain relationships. Okay, and so if I take, based on those material tests that we were talking about, on this axis, if I plot concrete stress, F'C, and I plot strain along this direction, this is the material that relates sigma over to epsilon. Okay, and if you remember, that defines the material nature of all materials. There's a curve like this for every material. Okay, and if you remember, for a while, what happens is that I get kind of a fairly linear region here. Okay, and the slope of that line, if you remember Hooke's law, sigma is equal to E times epsilon. The slope of this line, okay, is E, or Young's modulus. Okay, and that's a measure of this. Well, it turns out that E, where steel, E was taken as 29,000, or 29,000 KSI. Concrete, if you look, I've got a bunch of different curves for a bunch of different F'C values. I've got, F'C of 6,000 as the top line. I've got F'C of 1,000. You can see that E changes drastically as a function of F'C. Okay, the one thing that you notice that's fairly common across all of this is that for all of these curves, the peak stress that can be carried is taken as 0.002 inches per inch. And so we're going to start watching the strain as part of our calculations. This becomes a major characteristic that we have to constantly test and constantly evaluate. In fact, a lot of our safety in concrete is associated with the strain, right? Because the one thing that you don't want to do is you don't want concrete to fail by a crushing failure. We want more of a ductile failure so that it's, a more gradual. A crushing failure is often a sudden and violent end to a piece of concrete. Okay, now what you'll notice is that while this is the peak, it's not the ultimate, and so the ultimate strain generally occurs somewhere around 0.003 up to 0.004, and so this limit, this becomes kind of the magic number for what we call epsilon Cu, and this will show up on just about every strain diagram that we create for beams and columns. Okay, and this is assumed to be the limit of the strain. Okay, so what happens is you get kind of this, based on strains, a differing shape of this curve. And so, if we go back and where we're going with this is that if I plot the strain of a flexural member that looks something kind of like this, okay, what's going to happen on the stress is that according to this strain, if I limit this to 0.003, then I get a certain stress of 2 KSI. Plot something like this, but then somewhere down here is 0.002. Okay, and so according to that, I'm getting something significantly higher, and so my stress distribution starts to look something kind of like that. And so it's no longer, simple calculation. If I multiply this by the area, I can find the total force of the stress, but it's not located at any convenient point. And so we're going to make an approximation known as the Whitney approximation, but this becomes the stress distribution associated with concrete in compression for a flexural member. And so we'll be drawing these pictures or something similar, repeatedly as we start to go forward. Okay, now, like I say, the stress-strain relationship is straight or linear up to about 0.3 of F prime C, okay, and then it becomes a curvilinear function, okay, and a lot of this is due to, once I get past that linear point, I start to get into an inelastic state, or I start getting micro cracking that's occurring, and that will, like I say, for a while it'll continue to build up, but then it'll start to reach a point where it's so significant that the concrete starts to kind of break down. Okay, again, we talked about the maximum stress reached at 0.002, and that the ultimate strain is considered to be at epsilon C equal to 0.003, and again, that's for normal weight concrete. Lightweight's a little different, and there will be a correction factor that we want to associate with that as well. Okay. All right. So for concrete, the modulus of elasticity, again, we kind of drew one of those curves. You saw one of those curves earlier that I'm plotting stress. Now the stress in concrete is going to be listed as FC. That is different than F prime C. F prime C is taken as the 28-day strength. FC is the stress of concrete at any given time. Okay, and so if I plot stress versus strain for this, then this was that linear portion that we're talking about. This is the Young's modulus for concrete, and it's called out as an E sub C. All right, and so ACI in section 19.2.2 gives you the equations for what they will accept as the Young's modulus. Okay, for lightweight concrete, which is considered to be a concrete mix that has a specific weight somewhere between 90 pounds per cubic foot and 160 pounds per cubic foot, it's given by this formula: 33 times the weight, the unit weight of the concrete, to the 1.5 power times the square root of F prime C. And so I want to turn your attention to F prime C, the square root F prime C. Okay, in this, F prime C is always measured in PSI. Okay, so you might want to watch your units regardless of what's going on outside of this. And then the square root F prime C, you will see that over and over and over in concrete. Okay, we'll talk about different correlations, but this is kind of one of the major parameters associated with it. Now for normal weight concrete, which has a gamma of 150 PCF, pounds per cubic foot, then I'm going to be looking at doing 57,000 times the square root of F prime C. All right, and this will get you to an epsilon C measured in PSI. Okay, and so those are the two different formulas. So most often, for most structures, we're dealing with this guy, 57 square root of F prime C. Okay, so that's for our compressive behavior. Now, again, we talked about a little bit that concrete, the tensile strength of concrete is, something we're always keeping our eye on. It's a significantly smaller value than the compression limit. Okay, but this is also what's, driving where our force and the steel needs to be located, okay, or where the steel bar's positioning needs to be. So we're constantly looking at the different loading cases that produce tension in a particular element. So for uniaxial tension, we have our F prime T. So for tension, it's now an F prime T value. Okay, and again, in concrete, when we get into the actual design, we're pretty much going to be neglecting this because these values become so small. But for a uniaxial tension case, if that's all I'm doing is taking a bar and pulling on it, then I'm going to get a crack across the entire cross section. F prime T is taken as 4 square root of F prime C. And again, that's kind of an approximation, but that's kind of about where it falls. Okay, for a split cylinder, I'm taking a cylinder and I'm basically loading it along the diameter and producing a crack in which the crack is now pulling apart this way. Okay, the stress at which that occurs is called F prime S sub P, and it's equal to 2 times P, where P is the split cylinder load, over pi times D over L. Okay, and that's approximately equal to 6.7 root F prime C. Okay, all right. The modulus of rupture, though, is probably the most important for beams. Okay, and as we talked about, with that stress strain curve being something that looks as a linear relationship like this, where this is compression and this is tension, tension is where cracking occurs, and that's the way it was in all of these cases. Okay, so ACI 19.2.3 estimates the modulus of rupture, which is the stress down here at the bottom, our F prime R, as being 6 times the moment divided by BH squared. Okay, so that's just a simple rearrangement of sigma equals minus my over I again. Okay, and we're going to take that modulus of rupture estimate as being 7.5 times lambda, which is a correction factor for lightweight concrete. For normal weight, lambda is taken as 1.0 times the square root of F prime C. So 7.5 root F prime C will show up over and over and over in a lot of our calculations. Okay, all right. At this point, I think we'll go ahead and stop here. Okay, in our next lesson, we'll talk a little bit more about some of the time-dependent behaviors, which will be creep and shrinkage, and then we'll get into some of the reinforcing steel and reinforcing sizes for us there. But we're approaching a half an hour, so I think that's probably a good point to stop. So that's our basic concrete characteristics for the stress strain curve. So we showed you the stress strain curve in this, and how it's no longer a constant stress distribution, and so that will become a challenge that we'll have to resolve in one of the lessons coming up. And then, of course, E sub C, which is needed in deflection calculations and rigidity calculations. We've also talked about that. So anyway, thanks for tuning in, and we will see you all next time.